Hello, everybody. Thanks a lot for your interest in this presentation. My name is Wenbin. I'm the Chief Technology Officer of AnaSwift. AnaSwift is a company which provides efficient and high-fidelity solutions for modeling and design analysis of composite materials and structures. Today, I'm talking about a specific product of our company called WEBS. WEBS is a unique technology providing an accurate modeling for composite beams with the efficiency of traditional beam series, but with fidelity of 3D finite element analysis. WEBS was recently made available through Altair Partner Alliance. The WEBS technology was motivated by the need of the helicopter industry to provide an engineered solution for composite helicopter rotor blades. And the rotor blades are made of composites because of the excellent fatigue performance of composite materials. And the typical rotor blades could be several meters long and half meter wide. And the cross section itself could be made of dozens of composite layers for the skin and hundreds of composite layers for the spar, and also filled with other materials. And each composite layer is about 100 micron, 0.1 millimeter. So we have significant length scale difference. In principle, we can use 3D FEA to provide an accurate modeling. But to accurately predict the stress, we need to have at least one solid element per layer. Then, in view of the fact that each layer is only 0.1 millimeter, then you're talking about hundreds of millions, even billions of degrees of freedom for a realistic blade. And clearly, it's too expensive to be practical. And for composites, the most commonly used series is lamination series, but the rotor blade is really not a laminate, so this series is not applicable. And engineers usually use so-called smeared property approach. And what it does is to smear a stack of laminates to be an equivalent homogeneous solid. This is also called black aluminum approach. It can solve the efficiency problem, but it's not accurate. And the researchers also constructed beam models for rotor blades by introducing a series of ad hoc assumptions to reduce the original 3D problem into a one-dimensional beam problem. Usually, those ad hoc assumptions are valid for isotropic homogeneous beams, but not applicable for composite beams, particularly featuring significant heterogeneity and geometrical complexity. These assumptions will lose significant accuracies in the prediction. To avoid this disadvantages of this conventional methods, we come up with a new idea to deal with this problem. What we did is that we recognize the fact that cross-section is much smaller than the length of the structure. Then we take this small aspect ratio as the small parameter to carry out an asymptotic expansion of the original problem, original 3D elasticity problem, so that we can mathematically split the original 3D problem into a two-dimensional cross-sectional problem and a one-dimensional beam problem. WEBS is created to solve the two-dimensional cross-sectional problem, which provides all the cross-sectional properties needed for the beam analysis. After we done the beam analysis, we can predict the force and stress and deflections and moments. Then we can, using WEBS, to recover the three-dimensional displacement, stresses, and strains over the cross-section. To compute the inertial properties, we need to minimize the kinetic energy loss between the original 3D model and one-dimensional beam model. And The result webs provides is a 6 by 6 mass matrix. From there, we can recognize the mass per unit length and mass centers, mass moment of inertia. We can also compute the principal inertial axis. To compute structural properties, we need to minimize the strain energy loss of the original 3D model to the one-dimensional P model. And there are three commonly used engineering models for the beam theory, including the Euler-Bernoulli model, Tiamat-Sinko model, and the Velasco model. Euler-Bernoulli model is suitable for very long beams because it only captures four fundamental deformation modes: extension, twist, to bendings. The Tiamat-Sinko model is also applicable for not so long beams because it introduced two additional deformation modes to account for the transverse shear. When the beam is made of open thin-walled section, then we find out that the one variable for the torsion is not sufficient because that only describes the uniform torsion. And we also need to account for the restrained warping effects due to the open thin-walled section. So we introduce twist rate, and that will establish the Russell model. Because of the complexity of the geometry and also the anisotropy of composite materials, the stiffness matrix could be fully populated, which means that the corresponding beam analysis should also take the fully populated stiffness matrix. Webs can also compute the trapeze effect, which is the fact that the increased torsional stiffness due to the centrifugal force. Webs can also compute the neutral axis, principal bending axis, and shear centers for beams made of composites and with complex geometry, and can also recover 3D displacements, strains, and stresses. WebS is pretty unique and very unconventional, so users usually get confused what WebS can do. And because conventional beam theory, basically, you don't have a separate component like WebS, because people take assumptions, then it's a bunch of integration of the cross section. They can compute the beam properties. So what WebS does is take a finite element mesh of the sectional geometry and material as input to compute the beam properties, which is needed for a beam analysis code to predict the global beam behavior. Webs can also recover 3D displacements, strains, and stress over the cross-section. Webs can be used independently for structure design of beam sections, including geometry and material. For example, I want to maximize the torsional stiffness of the cross-section while maintaining the desired center of gravity. Webs also powers beam elements with the fidelity of 3D FEA for geometry representation and prediction with negligible additional computing time in addition to the traditional beam theory. And one point I have to emphasize that the beam elements should be modified to accept fully populated stiffness matrix. RIPES, although it's a computer code, but it's not yet another software. It's a unique technology, has more than 30 years of vigorous research as its foundation. It has been funded by US Army since 1988, which is 32 years today. It now provides a satisfactory solution for composite rotor blades. Currently, we are also under the support of US Army and US Air Force to further develop webs and put webs into more novel applications. And it now becomes a tool of choice for helicopter industry and wind turbine industry after so many years of extensive research. Besides the original application, including helicopter rotor blades and wind turbine blades, our users also applied webs to model propellers, eVTOL blades, and landing gears, high aspect ratio winds, and golf clubs, and tubes, rods, and columns, poles, and other structures. And as long as it's very slender, which means as one dimension, much larger than the two other dimensions, and we want to model as beams, then webs can provide a beam property for us to analyze this slender structure as beams. And we have extensively validated webs, not only in the practical applications industry, also in the literature. This is a critical assessment of computer tools for wind turbine blades modeling. We did this work more than 10 years ago, and we found out that webs consistently provide the best predictions for the complete sectional properties, not only the traditional beam constants, but the elastic couplings and the offsets. We find out that particular for the elastic couplings, the other tools are not predictive, even qualitatively. But webs, it's consistently provided accuracy as if you would like to model it using 3D FEA. We also validated webs with 3D FEA analysis, and this is for realistic rotor blade. Try to compute the thermal stress due to 100 degrees C temperature increase. And if we use 3D FEA using solid elements to model the structure, we're talking about 5 million degrees of freedoms. And if you use webs and we only need to carry out a two-dimensional cross-section analysis, we can get all the stress distributions with a particular cross-section you are interested in, and we can easily identify where the hot spots of the cross-section to have more quantitative assessment of the prediction of webs. We also take a load path and upstream load path to compare our prediction with the 3D finite element analysis code. We find out that the webs can reproduce all the stress components of the 3D finite element analysis. And what's interesting is that webs not only provides the longitudinal stress, which is usually a lot of beam codes will do, but also transverse normal stress and transverse shear stress. And we can get the complete stress and strain field, 3D stress and strain field, but with the simple engineering models and without the ad hoc assumptions used in other beam series. And it can achieve 3D FEA accuracy, and we can capture the plant level details of composite structures in seconds. Usually this is impossible using 3D FEA. And if we want to use webs for, as a component in the entire design workflow, then what we do is, for example, that for turbine blade, what we do is that we cut many cross sections along the span, could be dozens or hundreds. Then for each cross section, we invoke webs to compute the cross sectional properties for each cross section to put into the corresponding beam elements to carry out the beam analysis. After we done the beam analysis, then we can recover the stresses over this station and this station and this station to find out whether the structure is strong enough. And for realistic 3D structure, and usually 3D FEA can be used if we simplify it using shear elements, for example, for wind turbine blades. But it only used is it should be only used for the final design verifications because it's so expensive. And to enable webs and to increase its user friendliness, we recently integrate webs with hypermesh and OptiStruct. And we use the hypermesh to provide the pre-processing, and we implement webs as a dynamic link library for OptiStruct as one of the solvers for Altair products. And then we use the Hyperview to do the post-processing. For example, for channel for a beam, composite beam with channel cross section. What we can do is cut multiple cross section along this channel, and this channel, of course, could have different cross sections. Then we split the problem into the beam element, which is usually whatever existing beam elements in OptiStruct, and the cross section and no mesh. And each of them could have the corresponding data files. Then what we need to do is that we can, for each cross section, we need to invoke the webs library to compute the sectional properties as input for OptiStruct beam elements. Then we output the results. And because of the addition of webs, and we add new capabilities to OptiStruct and enhance the applications of OptiStruct. For example, that now we can analyze curved and twisted composite beams in a single seamless run of OptiStruct. And webs, and as an end user, you may not even know webs because it can be invoked internally with the right setup. And if we want to know the specifics of the enhancements, they can be grouped into three major categories. First, the OptiStruct can use that as a tool to load web's functions to compute section properties. And it can be done for Windows and Linux. And second, that the OptiStruct, we can identify particular beam elements and whose properties are computed by webs, then automatically invoke webs with the right setup. And thirdly, that for OptiStruct, we also enhanced its composite beam formulation. Now, the two noted C beam and C bar element can account for a fully coupled stiffness matrix, and also invoked for all elements when P beam L and P bar L has webs listed in the group entry. And as a conclusion, that the webs provides an efficient high-fidelity alternative of 3D finite element analysis for slender composite structures. For any structures have the cross section much smaller than the length of the structure, and you want to analyze as a beam. And the webs can compute the best complete set of beam properties is needed for any static and dynamic analysis using beam elements. It can also recover the complete set of accurate 3D stresses, which are needed for detailed stress analysis or strength and fatigue analysis. And is highly optimized for efficiency. We can capture the player level details of a real structure composite beam can be modeled and in seconds. And is also extensively validated in not only helicopter and wind industry, with more and more users join the user groups of webs. We find out that it's getting and more verified of the accuracy and also its usefulness. And it's also now directly integrated into Altair products. It is an essential piece of model scale simulation of slender composite structures to link the material properties to the structure analysis. So I'm very happy about the recent addition of webs into Altair Partner Alliance, and hope that the Altair users can take advantage of this wonderful technology to handle composite slender structures. With this, I want to close and end my presentation, and please let me know any of your questions. Thank you for your attention.